Hello and welcome to this video, which is all about moments. So a moment is the turning effect of a force. So if there is a pivot involved in the system or the object, such as here, this point down here is what we call the pivot, sometimes called the fulcrum, then the object will rotate about that pivot because it's a fixed point. And this force here will cause the object to rotate. And there are many examples of this in everyday life, such as using a spanner, for example. Now, the turning effect, or the moment, depends not only on the magnitude of the force, it also depends how far away from the pivot the force is acting. So, for example, if you applied the same force at this point, the turning effect would be different. Imagine trying to open a door by pushing near the hinge. It's much more difficult to open the door like that than it is from pushing where the handle is, for example, which would be over here if this were the hinge. So those are the sort of concepts we're talking about. So mathematically speaking, the moment of a force, or the turning effect of a force, is equal to the force itself, which is being applied, multiplied by the perpendicular distance from the pivot to the line of action of the force. And the line of action of the force is the line that stretches to infinity in both directions from the point of action of the force along which the force acts. So it's the line along which the vector arrow actually lies when you draw the force. So it's vertical in this particular instance. So you need to find a distance that is perpendicular to that line of action. So the line of action kind of goes down that way, and there is the perpendicular. So the distance that we're interested in goes from the pivot to the line of action of the force and is perpendicular with the line of action of the force. So it makes a right angle with it, like that one there. Okay, now in this situation that's straightforward, but what we have over here is a slightly different situation because the force is acting at this angle here to the object itself. But it's not the object itself that's important. Okay, it's the line of action and the pivot that are important, and that's what causes the moment. So in this situation, the distance is different. It's not this distance here like it was in the first instance. The distance is up in this direction because you can see as it hits the line of action of the force there, it makes a right angle there. It doesn't make a right angle. There's no right angle down here. So you effectively adjust the line of action of the force until, adjust the distance from the pivot until it makes a right angle and is perpendicular with the line of action of the force. Okay, so sometimes it's quite difficult to spot what the correct distance should be, and you need to think quite carefully about that when you're solving moments problems. So in both cases here, it would be FD, where this is F and this is D in this one, and this is F and this is D, with that right angle in there for this one on the right. Okay, so that's how you calculate a basic moment. But sometimes on an object or a system, there are more than one force. There's more than one force acting. So let's have a look at this situation. Okay, so we've got a pivot in the middle on this top diagram, and we have two forces acting. Okay, and now these might be because there are weights placed on the top. I mean, it might be a seesaw, for example, where you've got people on the top of differing weights. Now, in order to get the seesaw into balance, we have to adjust the distances away from the pivot until the moments on each side are equal. So here we have a moment from this force, which is acting at this distance here, and here we have a moment from this other force, which is acting at this distance here. So this force times this distance is causing it to turn this way, and this force times this distance is causing it to turn this way. Now we say that this is a clockwise moment because it will tend to turn the object in a clockwise direction. And we say that this one is an anti-clockwise moment because it will tend to turn the object in the anti-clockwise direction. So they say this is a clockwise moment and this is an anti-clockwise moment. If we look at this situation down here, we've got the same thing but in a slightly different configuration. So here's the pivot at the end of the object this time. We have a moment here which is caused by this force multiplied by this distance, and we have a moment here which is caused by this force which is acting at that distance D, both from the pivot. It's very important to always measure your distances from the pivot and always make sure they're perpendicular with the force action line like that. Those two are, so that's okay. So this one here tends to turn the object that way. So even though it's to the same side of the pivot, it's causing an opposite turning moment because this force is acting upwards and this force is acting downwards. So this one causes a clockwise moment and this one here will cause an anti-clockwise moment. Now, if the object is in equilibrium, then the sum of all the forces will equal 0. So putting that in clearer language, for an object in equilibrium, we say the sum of all the clockwise moments must equal the sum of all the anti-clockwise moments. So sometimes there are more than 2 forces acting, 3, 4 or more forces. So we work out the moment from each one and we add up all the ones that are tending to turn the object clockwise. We add up all the ones that are tending to turn the object anti-clockwise. And if the object is in equilibrium, the sum of the clockwise moments equals the sum of the anti-clockwise moments. So let's do a little worked example of that just to illustrate what I'm talking about here. So here is an object with 3 forces acting on it. Okay, we're going to say that the object is in equilibrium. It's being held up by a rope perhaps or something, and we have a tension in the rope which is acting at this distance from the pivot. So the line of the pivot is over here. That distance there is perpendicular, so that's okay. We have a second force down here, which is the weight of an object resting on the beam. So we're going to call that W0, which is the weight of the object. And sorry, that's an O for object, WO. And here we have the distance from the pivot that weight is acting, DO, distance to the object. And then we have a third force, WB, which is the weight of the beam itself, which is acting at a distance dB from the pivot. So the first thing to do when you're working out problems that involve the principle of moments is to pair up your forces and distances. Make sure you've got the right 2 in each pair. And I think it's very helpful when you're doing these problems to draw bubbles around them so that they're paired up. And if it's a complex thing, you might want to do the bubbles in different colours so that you can immediately identify what's going on. So that's the first thing to do. The second thing to do is decide which forces are causing a clockwise moment and which forces are causing an anti-clockwise moment. So in this situation, this one is going to be pulling the object in a clockwise direction, and both of these two are going to be pulling the object in an anti-clockwise direction. Okay, so that's your groundwork. Okay, that's the important thing to establish before you start doing any maths. Pair them up and figure out which ones are acting clockwise and which ones are acting anti-clockwise, and that will make your job a hell of a lot easier when you start writing equations down. So the first thing to write is that the sum of the clockwise moments equal the sum of the anti-clockwise moments for an object in equilibrium. Now I'm just going to do it in shorthand here. I'm going to say sigma CW, which stands for the sum of the clockwise moments, is equal to sigma ACW, which is the sum of the anti-clockwise moments. Now in an exam question, obviously you'd write that out in full. You'd write the sum of the clockwise moments equals the sum of the anti-clockwise moments for an object in equilibrium. You'd state the principle of moments in full, because that might actually get you a mark in the exam. But I think for general problems, you're safe just writing it down in symbols like that. Okay, so then you actually write the moments down. So we've only got one clockwise moment here, which is T times dt. Okay, that's it. Force times distance produces a clockwise moment, and that's the only one on that side of the equal sign. So on the other side of the equation, we've got 2 moments acting here. We have WB times dB, WB dB, that's one moment, plus, because it's the sum, WO times DO, so WO DO. Okay, so that's your equation with the quantities that we've got here, which represents the principle of moments. And after that, all there is left is to substitute and rearrange like we always do in a calculation question. So dt is 0.35, so 0.35 times t will equal WB, which is 20, times 0.2 plus WO, which is 12, times 0.1. So then we can divide through by the 0.35 there to give us T, and when you do the arithmetic on that one, you get an answer of T equals 14, whoops, just joined up my lines for me, thank you very much, 14.9 newtons to three significant figures. Okay, so if you do it in this way, it simplifies it quite a lot, and you can actually do it in one line of algebra and then substitution. So, but the important thing is to identify them first and figure out which direction they're acting, and then write down an equation that satisfies the principle of moments. Okay, so all problems can be done in that way. That's a very good sort of foolproof method for doing it. The difficult thing is to identify the distances sometimes when you've got angles. And the problems do get quite difficult. And it's also involved in equilibrium problems where you've got upward forces equaling downward forces and leftward forces equal right forces. But this is quite a simple one, which I'm kind of talking you through at the beginning. Okay, so let's have a look at the principle of moments in action in the real world. There's 4 situations I've managed to pick here. The reason you hike out when you're sailing a dinghy is so that you can balance your weight against the force from the sail, because the force from the sail is causing a moment in this direction, anti-clockwise, and your body is causing, or the weight from the body is causing a clockwise moment in this direction, and the boat will pivot around a point somewhere in the vicinity of the centerboard of the keel. Okay, so there's the principle of moments acting, and to keep the boat upright and balanced, you have to increase the clockwise moment in this case by moving your weight further out, increasing the distance from the pivot to the line of action of the force effectively. Here's another one. There's a classic example of the seesaw. You've got a force, which is the weight of this child, acting at a certain distance over here, there, and you've got a weight, which is this child, acting at a certain distance over here. The seesaw is tipping downwards because presumably, looking at this, the distances seem roughly equal, and therefore the weight of this child must be greater than the weight of that child, which is causing an increased turning moment in this direction, causing the seesaw to tip. This one down here is the final scene from one of my favourite films, The Italian Job, where, and this is a classic physics in action at the end of this film, with the gold inside the coach and the way it's just pivoted right on the edge of the cliff, and the guys inside are trying to save the gold. And finally, we've got a slightly more complex situation. We've got a pub sign here, which is in equilibrium, and the weight of the pub sign is causing a turning moment to try and tip the pub sign, or turn the pub sign about this pivot here, whereas the tension in the string, which is or wire, which is acting up in this direction, is counteracting that moment with a clockwise moment. So it's a slightly more complex situation, which we'll actually have a look at when we do equilibrium problems. And that's moments. Thank you very much.